This is the class for October 31st, 2013, class number 20. A couple of announcements just to begin. Remember, today is the deadline for submission of the Huntington Sanitary Board Project Stage 3. And the submission for that would be 2 maps printed out as PDF files with annotation, and they should be uploaded to MU Online by noon. And then the other announcement is the homework assignment that goes along with the material we're covering in today's lecture, homework 8, which is the Hydrographs assignment, is due on Thursday the 7th of November. Today we're going to continue the discussion of hydrographs and talk about synthetic unit hydrographs.
A synthetic unit hydrograph is sometimes used when we don't have the actual rainfall runoff data for a watershed. As I mentioned in class on Wednesday, the way that you generate a unit hydrograph would be to have both precipitation data and stream gauge data in order to make a real characterization of how a watershed responds to precipitation. You have to know how it has responded to precipitation in the past. And so if you know that during a certain storm maybe there were 3 inches of rain, and you know the duration of that storm and what the flows were, then you can go through the deconvolution process to generate a unit hydrograph. But sometimes it's just simply not the case that the data is available for a certain watershed, or maybe you do have a unit hydrograph for an adjacent watershed but not for the one that you're now interested in. And so synthetic unit hydrographs are an empirical way of generating a guess of what the response a watershed will have to a rainfall event. The shape of the hydrograph is triangular. It's not a very articulated view of what the response will be, but like a lot of things we do in hydrology, it's better than nothing. And so the synthetic unit hydrograph uses geometric or statistical procedures, and it's just an interpolation process where we start with some curve fitting data that may be regional coefficients that are known for an area, and we calculate a peak discharge for a certain unit amount of rainfall excess, and then we look to define the time to base. In the example we're going to work here in a moment, this is the shape of the hydrograph that we'll be characterizing. There's a step-by-step procedure that's provided in the text, although there are a couple of gaps in the explanation and the example even that they work. There are a couple of places where the units aren't clear, and you may need some additional information based on the homework assignment that you're going to get. So just to point out a couple of characteristics of this unit hydrograph. First of all, it's both a hydrograph, which is characterizing the precipitation or the rainfall excess in the case of a unit hydrograph. And so this part of the graph is showing how long the storm was. And then the watershed response is what's shown here in the lower part of the figure. And so it rains, or there's rainfall excess. Remember, just as a review, rainfall excess is precipitation minus the abstractions that a watershed has. And so for a certain amount of rainfall excess, we're going to be generating a hydrograph that says it takes a certain amount of time to get up to the peak, and then a longer amount of time for it to go down to the for the watershed to be drained. And you'll notice that what they're saying is basically 1/3 of the total duration is from the start of the storm up to the peak, and then it's 2/3 of the remaining duration is 2/3 of the total. So there are a couple of geometric parameters we're going to be taking a look at, and some of them have physical interpretations, others don't. The time to peak is from the beginning of the storm to when we see the highest amount of runoff at the outlet of interest. T sub PR, capital P, capital R, that's the time from halfway through the rainfall excess event until the time to peak. And so if the rainfall excess event was 1 hour long, and then that we calculate that the time to peak is 2 hours, then we'd say half an hour here, and then another hour from the end of the rainfall excess to the time to peak. So T sub PR would be 1.5 hours if we had a 2-hour T sub P, T sub capital P, and then a 1 hour rainfall excess event. One of the strengths of the Snyder synthetic unit hydrograph process is it allows us to easily calculate a unit hydrograph for a storm of any duration. In the example that we've worked previously in class where we were using a unit hydrograph, remember the unit hydrograph was for a rainfall duration, or rainfall excess duration to be more precise, of 1 hour. And so we were able to, for a storm that lasts 4 hours, we could just basically have different layers. We repeated that 1 hour hydrograph 4 times, and we had the different columns that then we added up. But it would have been more difficult if the precipitation lasted less than the 1 hour. The unit hydrograph, we'd have really no way to apply that unit hydrograph that was based on 1 hour of rainfall excess to a storm that would be shorter than 1 hour. The Snyder synthetic unit hydrograph process allows us to generate a unit hydrograph for any duration of rainfall excess that we happen to be curious about. So here's the example that we're going to work here in a moment, and it'll be a pencast that I'll embed into this video file, and so you can work through it independently and or just watch as I do it. This is a watershed where the area is known to be 5.42 square miles. The main channel length, and so the length of the channel that has the greatest flows and exists for the longest duration, the longest length up to a certain upstream area, and so maybe what we're showing is that it requires maybe half a square mile of upstream area before any channel forms. And so we go the furthest point away from the outlet to where channel begins to form, and that length is 4.45 miles. This L sub P is a little bit more abstract. That distance is how long from the outlet to the centroid of the watershed. In the book they describe it as a mirror image distance from the outlet to the point opposite the centroid, but essentially that's the same thing as saying the distance from the outlet to the centroid of the watershed itself, and so the center of area, and that accounts for the shape of the watershed. And a long skinny watershed would have a longer L sub C compared to a more circular shape L sub C. In this example that we're going to work, the C sub T and the C sub P are regional parameters that have been derived from an analysis of adjacent watersheds or estimated statistically as described by the book. And so the two things that we're going to find in this example are the standard duration, which is a starting point for using the Snyder method, and then we're going to use that standard duration and the rest of the process to find out what the hydrograph would look like for a rainfall excess duration of 30 minutes. So in other words, we're going to want to generate a hydrograph that says if there's 1 inch of rainfall excess, this will be the hydrograph that comes out. Alright, this is a Snyder synthetic unit hydrograph example. We're going to be going through a step-by-step procedure that is identified in the book but is not explained in much detail. In this example, we first have to, as step 0, identify the known parameters for the watershed. This is a watershed of area 5.42 square miles. The length of the main channel is 4.45 miles. The length of 2.0 miles refers to a distance between the centroid of the watershed and the outlet. It accounts for the shape of the watershed, so that a long, skinny, narrow watershed would have a longer L sub C than a round watershed that's more compact. C sub T and C sub P are factors that are regional factors that can be estimated based on analysis of other watersheds, and the book goes into a little bit more detail of how these regional factors are derived. So, step 0. Step 1 is to first calculate the standard time to peak. Okay, and the formula that's given for that, T sub P is C1 times CT L times LC to the 0.3 power. Okay, for
units of traditional units, this C1 is 1.0. And thus what we'll substitute in is 1 times the C sub t of 2.0, 4.45 times 2.0 to the 0.3 power is 3.853 hours. And that represents the standard time to peak. The standard duration, formula for that is T sub r is Tp divided by 5.5, 3.853 hours divided by 5.5, so 0.70 hours is the duration. This is the standard duration and the standard time to peak. In this example, what we want to do is find out what the unit hydrograph looks like for a desired duration of 30 minutes. So essentially what we're saying is, what if it was a storm that lasted 30 minutes? So we're going to have to go through a transformation procedure. The typical duration and time to peak is what we've just calculated, and so we'll transform that into a time to peak for a desired duration, and that's step 2. And that is TPR in capitals. Time to peak plus 0.25 T capital R minus TR. Okay, we've already calculated 3.853 hours for T sub P plus 0.25 times 0.5 hours. So this T capital R is the desired duration. Desired duration T sub R equals 0.5 hours, since we want to say that for a storm that's 30 minutes long, minus 0.70 hours is the standard duration. So that is 3.803 hours is the T sub PR. There's a diagram in the book that shows the hydrograph of a storm and then the triangular shape of the unit hydrograph. And so what we've just done is found that the time, the T sub PR is the distance from the middle of the hydrograph to the peak of the hydrograph. And the amount of time that elapses from halfway through the storm to the peak of the hydrograph itself. So just to illustrate that, here's time, and here's Q, and we're going to end up with a hydrograph shape that's triangular like that. For some rainfall duration, this is representing how long it's raining. From the middle of the rainfall to the peak, that represents the T sub PR of 3.803 hours. That's just been calculated. And step 3 is to find the peak discharge. Q sub PR. And the formula that's provided for that is Q sub PR is C2 CP A divided by T sub PR. Alright. Again, because of the units that we've got, we are given that C2 is 640 for BG units. Had we been working in SI, it would be 2.75. Okay. So making that substitution, 640, 0.625, and that C sub P is one of the regional expressions, regional coefficients, divided by the 3.803 hours. Okay. 570 CFS per inch. Remember that a unit hydrograph is in terms of a unit of rainfall excess. And so here, for every inch of rainfall excess, there will be 570 CFS as the peak flow rate. Step 4 is to find the width of the unit hydrograph at a certain point. We want to know if this is the peak flow rate, at half of the peak flow rate, how wide is the unit hydrograph, and we're going to use that to allow us to estimate the total duration of the unit hydrograph. And so this W50, the width of the unit hydrograph at half of the peak flow rate, C sub 50 Q PR divided by A to the 1.08 power. All right, C sub 50 is 770 for BG units. And had we been in SI, the units then would be 2.14. Okay, so the W50 is 770 divided by 570 CFS per inch divided by the area, 5.42 square miles to the 1.08 power. And what comes out of that is 5.045 hours. So that's telling us how big this distance is. We also need to calculate W75. It's also going to be used to calculate the total width of the storm. So W75 is C75 divided by QPR divided by area to the 1.08 power. And the C75 is 440 for BG units. Had we been in SI, then it would be 1.22, the factor that we should substitute. So 440, 570 divided by 5.42 to the 1.08 power. And that works out to 2.883 hours. Okay, in the fifth step, we now get to calculate the width of the hydrograph, this T sub B. So, how long does the unit hydrograph last? And the formula for that I'm going to write in just a moment, but before I do, what I want to show you is where one of these coefficients, how it's derived. And so, in the formula that I'm about to show you, there's this factor of 2581, and the units for that aren't mentioned in the text, but what the units are is cubic feet per second times hours divided by square miles. So that if you multiply this by area in miles, divide by flow rate in CFS, then you'll get hours. This is for BG units. If you are working in SI units, then the equivalent factor would be 11.11 cubic meters per second per times hours divided by kilometers squared. And that is for SI units. In this case, we're working in the traditional units, and so the equation that we're going to have is T sub B is 2581A divided by QPR minus 1.5 W50 minus W75. 2581, 5.42 miles divided by 570 CFS per inch, which we previously determined, minus 1.5, 5.045 hours, and 2.883 hours. That gives us that the T sub B is 14.09 hours. So with that, we're able to know both the peak flow rate was Q sub PR 570 CFS per inch, and then that base time was 14.09 hours. Remember that a unit hydrograph is specific to a certain watershed, and so it's just this watershed where an inch of rainfall excess would give this peak flow rate, and where the base time would be 14.09 hours. And in fact, not only is it specific to this watershed, but this unit hydrograph is specific to a rainfall excess period of 30 minutes, because you'll recall that we found out, starting with the standard time to peak and standard duration, we found out what would the unit hydrograph be for a rainfall duration of half an hour. So if we had a storm that we wanted to look at what the watershed would do over a 2-hour period, then we could use this transformation procedure to find a synthetic unit hydrograph for whatever duration we were interested in.